Gravity has been the very first scientifically understood force discovered by Sir Isaac Newton, and his equation that describes this force is an accurate prediction that we still use today. Yet there is a problem. While his laws describe the strength of gravity with great accuracy, Newton still has no idea how it works. In the early 20th century, there was a patent clerk in Bern, Switzerland named Albert Einstein. Einstein thought that if an object falls towards the Earth, the object experiences free fall since gravity will be the only force acting on it. And this would be no different than being weightless in space.
In a way, gravity and acceleration were different ways to describe the same things. Einstein had huge insight about how to connect gravity with the theory of relativity, and this was through the idea of acceleration since gravity and acceleration are equal.
Imagine you're in a room that has a bathroom scale. What will happen if you step on the bathroom scale? Well, if you're anywhere stationary on the Earth, then the scale will obviously record your weight. But if you are in a room of a spaceship moving at 9.8 meters per second squared, then the bathroom scale would still read the same as it did on Earth. Acceleration inside the spaceship will be distinguishable from being stationary on Earth. If you didn't know that you're in a spaceship, you will just presume that you're still on Earth. There'd be no way, or would there?
Einstein thought about this by asking himself if there's a way to tell the difference. If you are riding in a spaceship accelerating at 9.8 meters per second squared and point a flashlight on the other side of the room, Einstein finds out that the height of the light on the other side of the room is shorter. This is because for the room when you're rushing up in even faster speed as the light is propagating across the room, since the room is accelerating upward at 9.8 meters per second squared, the light beam would appear to be curved downward.
However, if you are on Earth, this will be no different because the acceleration of a room in a spaceship should be no different to the room under the influence of gravity on Earth. He realized that the light bends as it travels across a room because light always takes the shortest path between 2 points, which is going straight. He thought maybe the light is taking the shortest path between 2 points and the shortest path may not be a straight line.
And in space, Einstein hypothesized that perhaps a straight line is not the shortest path between 2 points, and with the presence of mass and energy, space becomes curved. Hence, the shortest path that the light can take is a curved path.
Let's take for example this model. This whole thing represents the space. If you put a heavy object at the center, what can you observe? This cloth curves at the region where the heavy object is placed. Now, I will let the balls roll on the cloth. You will observe that they are somewhat revolving around the heavy object. These balls represent the planets that revolve around the sun. If light rays coming from a distant star, according to the Newtonian motion, it will move in a straight path like this. On the other hand, Einstein's theory states that light rays follow a curved path, just like we see here. If this is the case, the light coming from a distant space will pass the sun and could be bent through space, and the stars could appear to us on Earth, apparently at this location.
This is how Einstein visualized his concept about space and his general theory of relativity.